PWM, DC-DC power conversion, right? So basics, not basics, basic concepts of PWM, DC-DC power conversion. And let me go back to the previous page. So we are dealing with PWM converter, and the counterpart of this PWM converter is what? As resonant converter. Okay, there are two types of converter: PWM converters and resonant converters. So resonant converters, we studied this in the last semester. So it's rather complicated and difficult to understand, and also difficult to teach, because that technique is not fully developed yet. That means this PWM, DC-DC power conversion, or PWM, DC-DC converter is fully investigated. So everything is known, right? So this converter is fully matured. Okay, so this one is very, very systematic. Okay, so everything is discovered by some researchers, and I have a full knowledge about this, not 100%, but very good percent of this part. But resonant power conversion is not fully understood yet, all right? Particularly the dynamics and control is still under development. Still there are people working on that topic, so that topic is not fully matured. Okay, so it was not easy to teach or to learn that topic, but this one is different. Everything is finalized. So we only discussing the known and the concrete result of previous analysis. And these resonant converters are under matured. Okay, so we discuss the basic concepts of this converter, this power conversion. So let me take one example. This is the example I'm using all the times when I introduce the techniques of PWM power conversion. So I used this for the undergraduate courses, and I used the graduate courses, and I used this example for the industry peoples. Okay, so let's assume this. So we are trying to energize this string of the diode. So this is LED, light emitting diode strings. So 4 of them are connected in series, and the load is this one. It requires exactly 12 volt. That is the assumption. Practically, there is no such a requirement in practice, but let's assume this works at this voltage at exact 12 volt, and the source of this DC source is batteries with variable out voltage. You know, this maybe typically this is out voltage of this battery is 24 volt, but depending on the status of charge and some environmental things and temperature, the voltage will be varied from, for example, from 18 to 30 volt. And we want to regulate this voltage at 12 exact, right? So this is battery, and this is LED strings. So in between, we need something, okay, that controls the voltage. So we are using this variable resistor. So it's called conventional resistive solutions. So assume this is the variable resistor, and here is just some branch, and this is the controller, and we assume this current is negligible. So controller is taking the almost the zero current. So I through this controller is negligible. Okay, then this is the resistance of this LED thing, and this is the RX variable resistance, and this is the RD of resistance of thing. Then controller is this. This is the simple voltage law here. So our voltage across this diode string is, this is the voltage division. This is battery voltage. This voltage should be 12 volt. Okay. So if this voltage, the battery voltage is increased from the previous value, then this one is increased. Okay. Then this one should increase too, right? So the voltage drop here is increased. So the difference between this and this becomes this. So this will maintain at 12 volt. Okay. This is very simple, right? And actually, you have seen this device is called voltage regulator. Looks like this. So it's written here, 7815. All right. Then this this terminal is A, B, C, and there are three terminals: A, I don't know, B, C. All right. Okay. So it senses this voltage here is larger than this. Then increase resistance here, so increase voltage drop to make this voltage regulated at 12 volt, right? So this is the principle of this. Actually, you are not using this variable resistor, so active device works as variable resistor in linear region. Okay, you have seen this. You are using this a lot. Okay, but this is good. But this is basically this resistive solution, and it has very serious power loss problem. For the small power application, it's okay. But for the large power, this power loss can be very large. Okay, so ohmic loss at Rx here is PIN minus P out, and this is IO as current through this battery and this LED string. Okay, this is VB, so input power. Output power is current. It's the same because this controller current is negligible. So this is the power loss at Rx. There's a difference between this and this. This is written here, right? This loss is proportional to this current. Okay, so if you use large current, then loss will be large. And it is also proportional to the voltage difference between this and this, right? So there are some technique to reduce the voltage difference between input and output. It's called low voltage regulator. That is basically this resistive approach. Okay, so let me take one example. So problems of this resistive solution. So let's assume this is a diagram of previous resistive solution and operational. You are trying to evaluate the efficiency of this system. So operational condition, assume battery voltage is 30 volt and the power through this LED string is 60 watt at 20 volt across this 4 LEDs. The voltage drop is exactly 12 volt. Then this is our power. Then current is 5 volt. Okay. Then power loss is IO is 5M and IO is 5M. This is voltage difference. This is power loss. Okay. So this power loss 90 watt is even larger than the rated power of this LED. Okay, so efficiency is less than 0.5. So this cause huge problems for some applications. Right? Every power loss should transform to the heat. Right? And heat should be removed, properly removed. Otherwise, heat will continue to increase until it destroys the semiconductor devices. So cooling system is required, but the cooling system usually consists of some fans and heat sink, which increase the weight and the size of the LED drive circuit. All right. The primary concern here is power consumption. Saving of power is not a main matter. All right. So the main matter is comparability of this converter with your electronics, portable electronics. Suppose this is cell phone. So if the power supply of this cell phone is as heavy as this one, nobody will use this. All right? So they are not comparable with modern portable electronics. But this previous, we have another alternative solution. Then their efficiency can be 100%. Ideally, that is fully comparable with any portable, small size or low profile electronics. Okay, so this is big problem in the space power system. We'll discuss the space power system very shortly. Okay, very small part of that later. All right, so you cannot use, mostly we cannot use this, but there is one particular application. Still this resistive approach is used. That is what? Audio amplifier. So the audio amplifier should reduce any ripple component, harmonic component, or any noise it generates harms. Okay. So for the quality of the audio, still they are using this type of power supply. So they are heavy, right, and big. Okay. So we have alternative solution here. The situation is the same as the previous resistive case, but in here we have this part and LC between this battery voltage and this LED string, the load, right? And here is also controller. So it is a little bit complicated compared to the previous resistive approach, but it has biggest advantage. Okay, so this part is called SPDT switch, single pole double throw switch. Let me put this here. Okay, so this is very, very important device. So details about this is coming later. So assume this for the fixed switching period TS. This switch is connected to this. Okay, maybe this terminal will be referred to as A, and this terminal is referred to P, right? And during the fixed TS switching period, this switch is connected this port A through A for T on, and it is connected to P passive through for the remaining part, right? So the voltage here is something like this. When this switch is connected to the A, this Vx is same as Vb. When this switch is connected to this passive terminal, it becomes 0. All right. So this is pulse waveforms. So this DC voltage is converted to the pulse waveforms, and you have LC. You have some resistance here. Then it consists of low pass filter, LCR, low pass filter. So low pass filter is just filtering out this voltage, and the average value of this will be generated here. All right. So this DC voltage is converted to another DC voltage. Okay. This is the basic principle of PWM converter. So we discuss this little bit further. So first, frequency domain analysis. Let's consider the frequency domain analysis. So this is a periodic waveforms. So Fourier series of this contains the DC component and is a 0, and fundamental component and second harmonic, third harmonic, so on. Okay, so omega s to omega s, there is distance here, and omega s is this one, switching frequency. So 2 pi divided by Ts. Ts is the switching period. Okay. So if this filter is ideal, that means this L is infinite, or C is infinite, or both of them are infinite. Then you have this kind of filter characteristics. Okay, so only this DC component is passing through this. From here, pass from here to there, unaltered. Okay. So this is the ideal case. But in practical case, this will like this. This is the real low pass filter. Then there is just this component part of this higher order harmonics will pass through. So this is practical case. Okay. So this is the time domain interpretation of ideal case and the practical case. All right. So let's think about the time domain. Let's think about everything in time domain. Okay, so voltage here, Vx is coming here. Okay, then Vx is this one. In time domain, this low pass filter is just taking average value of this pulsating pulse waveforms. So for the ideal case, this average value of this DC value will immediately appear as the output voltage. So this is the ideal case. All right. But in reality, if this value, they are not infinity, these values are not infinity, then output voltage will follow this during this time period. So, okay. During this time period, it follows this, follow this, follow this, and follow this. All right? So eventually it will go something similar to DC, but not perfectly DC. Okay? So this is the voltage waveform for the practical case. So this is for the practical case. That is shown here. It's called the ripple component. Okay, so you know the ripple. This is the surface of some pond, lake, and if you see this in distance, it looks like a horizontal line. But if you approach to this spot, there is just some ripple component, something like this, right? So we try to minimize this as small as possible, right? So this is called two-step. Actually, there are two steps in DC voltage conversion. First one is conversion of this DC voltage into this pulse waveform, and second part is just filtering out this. Okay, just taking the average value of this, or just passing, just taking the DC component in Fourier series expansion. So this one is that simple. And the control law is you want this one as constant as possible with the minimal ripple component. So our voltage is almost DC, and that value is average value of this voltage. And we use overbar to represent the average of something. And this is the average weighting factor, because this is the TS, and it has this value only, this period. So weighting factor. It's called Dury ratio, Dury cycle of active switch. Okay. Some student, particularly Korean student, they call it ratio. Ratio is something else. Okay? No. They call it Dury. Okay? Dury is something else. Dury ratio. All right? So you should call it Dury ratio, not Dury. Dury ratio of active switch. Then there is no power loss. Okay? So in here, there is no power loss, because if SPDT switch is ideal, there are no power loss. And this reactive component, if they are ideal, does not take any power. So in theory, this efficiency is 100%. Then all the problems associated with power loss, okay, heat generation and requiring of the heat sink and some fans, they are gone. All right. So this